Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, we discussed a lot of things and now it's time to go in detail into the parsing. Before going into the actual techniques in the parsing, we have seen that the parser on the left, it takes the tokens, right? But on the right, it gives you abstract syntax tree, AS tree, as an abbreviation. Now, question is, we talked about the parse tree. So what is the difference between AST and the parse tree, right? So here we go, the parse tree versus the abstract syntax tree. Parse tree contains all tokens. It contains those which tell us about the nesting structure and all those things, right? Now, like we have parentheses, like we have curly braces, okay? So it traces the operation of the parser, okay? Because it captures the nesting structures, but there are too much of information, like parentheses and terminators. We may have semicolons and all those things. So a parse tree actually shows a concrete structure, okay, because it traces the derivation of a sequence of tokens. Now, an abstract syntax tree, on the other hand, does what? It abstracts away all those artifacts, like it flattens the tree hierarchy. It drops those tokens, like we have the parentheses, like we have the terminators and whatever it is, okay? So AST shows abstract syntax, what we say abbreviated as AST. Now let us see it with an example, okay? Say, for example, we got a grammar, E. Let me, our grammar is, we got an expression, and we say, hey, either it is gonna be the int, or it is having the parentheses E, or it may have the E plus E. Very simple grammar, which gives you the addition of the two integers. Say you got a string, for example, 3 plus 4 plus 5. Now this is our syntax. This is our string, and we want to build what? After parsing, we will have a parse tree, right? So parse tree will start from the E, start symbol E. Now after that, it will try to use some rule. Definitely will use the E plus E. So it's gonna use the E plus E, okay? After that, this E, it will go into the, and it will use the first rule, say int, that is the int of 3. So for example 3 it was. Now then this E will be used as parentheses of E. It will expand it because I want to match it with this string. So we have to see how exactly the parse tree works. That's the techniques we will be using. We'll talk about that, okay? Now this thing will not be written like this. Okay, it will have rather three children. One is the open parent, E, and closing parent, right? And after that, this E will be expanded to again the 3, that is E plus E, because I want to match it with the my string. So then I will have here the int, and this guy also with the int. And if you see here, there's a 4 plus 5. Say this is the int 4 and int 5, right? Int 4 and this is my int 5. Now if you look at this parse tree, it has a lot of information, which I really don't know need as a as a programmer. When I want to convert it into some sort of intermediate code, I really don't need all these things, because it talks about those parentheses and all those things. If you look at here, I really don't need this thing. I really don't need this thing. I really don't need this thing. Neither I need this thing, right? Nor this, nor this. I'm interested in this guy, this int 4, this plus, and int 5, right? So if I do it in a little different fashion, let me change my pen. Make it something like green. Okay, so I may need what? I may need only a few things here. So maybe I will use this plus as a node, I will this plus, I will say, hey, this is my, say for example, this guy, this is my this plus, okay, and I may have two children of it. One is talking to the int 3, so that is pointing to some int 3, and another guy pointing not. I will skip all these things, I will skip all these things, right? Okay, I will skip everything of it. So I will say this is pointing to another plus, this plus, right? So I make this connection here to this plus, this with the int, and another connection to the plus. So I will have another connection to the another node, which is again a plus, and it has two nodes, left and right children, and the left one of this plus is this 4, and the right one is this 5. So I will say left one is this 4 and this one is this 5. Okay, now you see it also captures the nesting structure, right? So we see by this, now this is my AST, abstract syntax tree, which is more concise, which is more perfect, more compact, and it's abstract from the actually the concrete structure. I'm not I skipped all that concrete structure. That's why we call it abstract, because it abstracts from the concrete syntax, right? It is more compact, is more easier to use, right? So this one will be the data structure which we will use in a further for the further processing of a compiler. Now let's talk about the parsing techniques. When you talk about the parsing, okay, we have a parser. A broader scheme got two types of parsers. One, whether it can be either top down parser or it can be bottom up. Okay, when I say top down parser, let's first take the top down parser. We have first thing what's called as a recursive descent. This is how we actually parse. Now in the recursive descent we may have what's called as the backtracking. We'll discuss this thing in detail now. And then there are something which while we don't have a backtracking, we have non-backtracking. And when we talk about non-backtracking, what we have is called as the predictive parser. And the example we have in the predictive parser is the LL parser. Okay, now there are many things, when you say top down parser, and where we have backtrackings, we have the non-backtracking, where the predictive parser. So basically we got two guys on the backtracking parser with the where we have backtracking, and then with the parser we have predictive parsers. So let us take a top down parser. The first one will be the recursive descent, where we have the backtracking. Okay, so this will be the broad picture I'm talking about. Let me change the pen. Okay, now we have a recursive descent. Okay, we will remove the left recursions also here. So here we will also remove the left recursions. So we'll see what is the left recursion and what's its role here, why we should remove it. Okay, we have to also do the left factored grammar. Okay, what is the left factored grammar? We have to talk about those things also. Then when we remove the backtracking, we will remove even the backtracking. Now this will be in the backtracking, we will remove the left recursion all, but here we will remove the backtracking. Okay, remove backtracking. When we remove the backtracking, we will lead to the predictive parser. Okay, and a predictive parser, we can then use the non-recursive predictive parsers. We can use the non-recursive predictive parser, and we will be using here the tables, and basically we remove the recursion. So this is a broad picture. We will come back to it time and again. Let's first take up the recursive in the top-down parsing, the recursive descent. What is recursive descent, and what is backtracking? Okay, and then we talk about the left recursions, and we try to remove the left recursion. So first these three things: recursive descent, and what is backtracking, why we have a backtracking in it, and then what is the left recursions. Now let's talk about the top-down parsing by recursive descent. Okay. Now now in a recursive descent, what we do is we parse tree, which we construct actually is done from the top and from left to right. Okay. So we start from the top, and then we start from the left, and then we go to the right. Say we'll explain this in an example. Say we have a grammar where we have the star symbol e, then we have t plus e, or t goes to int and int into whatever. Then let's try to build a parse tree for this input string where we got int 5 into 2. Okay, so we're gonna start from the e. Okay, and we basically start building our parse tree in order. That means if we have this thing is structure, so we'll start from the root, from the left, then we go to the root, and then we go to the left, right? Then we go to the right. Sorry, we start from the left, we go to the root. So when we serve the left, when we are finished with it, if there is something, we finish that. Okay, when we finish with this thing, then we come back here, and then we go to the right side and other side. This is what in order says. So if you want to build this, so how we do this, and we see why we do the backtracking, because we have to use the grammar rule. Okay, so when we start from the e, we start from the first symbol, that is the e. Okay, so we have to choose the production. So definitely the production will be here, and say for example we got int 5 and our pointer is here. We're just talking about the first input token. We will try to match with our grammar. Okay, so we have to use the production rule. So so first production rule is t plus e. So I will use the first production rule, that's t, when I start building my parse tree, t plus e. Okay, now what we do is when we see a non-terminal, okay, we use the production rule, and when we see a terminal, we try to match it with our input token. Okay, so input token is int 5, and we have to match it when we are to match when there is a non-terminal. When there is a terminal, when there is a non-terminal, we will use the production rule. Now in this case, if you see here, we have used firstly the production rule, that is this guy, t plus e. Okay, the first production rule, and we try to use that e, so t plus e. Now we have to use in order, because in order says first go to the left. Okay, and when I go to the left, and I'm seeing it is still a non-terminal, that is t, so I have to use a production rule. So I will use the first production rule, because t is first production rule is int, so I will try to make it an int, right? Okay, now this int is a terminal, so when I see a terminal, I try to match it with my token stream. My token stream pointer is here, the int 5, it's matching, so it does match, so good. But what is after that is a plus, and when I see my I advance my token pointer, that is the multiplication, which is not a match, so that means this thing is not going to work. Okay, so what I try to do is I will try to use another production, that is int into t. So if I use here int into t, again the same story will be, because int will match. Okay, but multiplication will not, multiplication in this case here, because there is a plus here, and this is not going to match with my asterisk, so this is also not gonna work. Okay, so what will happen is I will try to go on and go on with the t. Okay, so that means when I put all the production rules here, and I see that hey, this is not gonna match, because definitely if I use this then this is int into t something, then there is a plus which is not gonna match later on, because it will try it, or it will try all these options, and when it see later on no, it's not a match, it's gonna backtrack. Okay, so like we did here, this is what backtracking means, that we use it the int firstly, and we try to see the plus it doesn't match with the asterisk. So what I do is we backtrack, we say no, it can't be there, so let us try to use some different production rule. Okay, and when that doesn't mean that doesn't match, we backtrack, we use another production rule. So we are done here, so nothing matches here, so we have to go back to our to this step. So what we do is we backtrack, we say though this is not good, and even this is not good, so we have to use something else. So we backtrack to the E, we backtrack all steps back. Okay, so we will be using this rule now instead of t plus e, because we have done the t plus e and we saw this doesn't match. So what I do is we will use the next thing now. So we will use te goes to t. Okay, now this is not a terminal, this is a non-terminal, so we have to use the production rule of t, and we will definitely use the first one. Okay, which is the int. When we see the t as an int, and t goes to int. I have to take my pointer back also here, because it's gone back. So my pointer is back at this int. So when we try to match it, because now we have a terminator, okay, so we try to match it with our input string. Now it does match with the int 5, but after that there's a multiplication and there is nothing in it. So what I do is we have to backtrack again. So we have to backtrack here again. So we can't use the t, rather we use the next production, that is the int into t. So here we can't do this, we have to backtrack again. So we backtrack here, we start it again at t, e as int multiply and t. Let me make it properly. So e actually goes to t first, yeah, then t actually has to use the production rule, int multiply it with the t. Now on the left side we see the non-terminal, so we have to match it, and it's matching with our int, this one is matching here, so it's okay. We advance to the multiplications and it also matches here, the multiplication also matches here, and we advance to the t. Now t is a terminal, because we go to the left in order, we go from left, then we go to the right. Now t is something, the non-terminal, so it is a production rule, so definitely we use the first production rule. Okay, and that is our int. This is the first production rule to be used. Okay, so we will make it as an int, and definitely now this is a this is a terminal, so we have to match it, and it's matching my token stream, that is this pointer would have in here now. So because multiplication was matched, so it matches, so everything matches, we are done and we are happy, right? So you can smile a bit. So this is how we do the backtracking and all. So let's take another example, very simple one, so that we understand it properly. Let's take up same grammar. So we have a grammar that is, say for example, e goes to t or t plus e, and we got a t, it goes to the either to the int or int star t, or just simply the parent size at e. Okay, and we got token stream, a simple token stream of int 2, for example. This is my token stream. I want to match it, so first pointer will be here, the parentheses, and I'm going to use the parse tree. I start from the e, definitely I'm going to start from the start symbol e, and I will try to use the first the production rule, that is the t, is it or not? So definitely e goes to the t. Okay, and now this is a non-terminal, so I can't match it with my input stream. I have to match, I have to use the production rule. So definitely I'm in a t, I'm gonna use the first production rule, that is the int. Now when I see the int, it is the terminal, and I have to match it with my input stream, which is the first start parent. Now start parent and int, it is totally a mismatch, so I have to backtrack, isn't it? I'm gonna backtrack. So what a backtrack means, I can't use this production rule here, so I'm gonna backtrack here. So I will say that I can't use this. So what I do is I will try to try my hands on another production rule, that is int into t. So I'm gonna use int multiply by t. Now on the left side, because in order I'm gonna do in order is the int, and I try to match it with my input stream. This is my input stream, right? So I have to use this input stream. It doesn't match, so it's again a mismatch because int is not gonna match with the parent. So I'm gonna again backtrack, so I can't use this rule. So I go backtrack, man. I can't do this. So I can't do this, so I have to use another I'm done with this, so I'm gonna use the next production rule that says e and closing parent. I go in order and I try to see this one. This is a terminal, so I have to match it with my input stream, and yeah, it's match, so it's a perfect match. So I advance my input stream to the int, okay, to here I match it with my int, and I advance this here to the e. Now because e is not a terminal, so I have to use the production rule. So I have to use, because I'm starting again, so e, I have to use the first production rule, so e goes to t. Okay, now t is again not a terminal, so I have to use the production rule. So I get the first production rule, so that is int, t goes to int. The moment I saw the the terminal, I try to match it with the pointer where my pointer is on a token stream, that is int, and it does match. It does match. Okay, so I advance. I say okay, it does match. I advance my token stream to the here, that is the right parent now, and I advance here because I'm done here. So I have to go to the right side. So that's this guy, and it's the right parent, and it is exactly matching to my input stream. Okay. So that means I am done with my parse tree. So this is going to be my parse tree, which matches the input stream. And since my input is ended, so I accept this token stream, right? So this is what is called as a recursive descent in a top-down parsing. We did a top-down. We started from the top and go to the bottom, and we did it to the left to right. Okay, and what we did is we recursively descended from left to right, from top to bottom, left to right. Okay, let's take another example of recursive descent where we use backtracking. Say for example grammar, we're gonna see then variable ad and bd or bd, and a gonna be ab or a. I want to find try to have a string cad and try to build a what is called as parse tree for this. Now firstly we're gonna use with the start symbol s. Okay, that is an s. So we'll start with the start symbol s, right? And that's my s here. Okay, and we'll see the first rule, that is the cad. That's the first rule I have to use. The first rule, that is the cad. I'm using c a and d here, right? And s goes to cad. Now a is the capital A, that is the non-terminator, and I see the c, which has a match with the string here, right? It has a match with the c. Then a, after a I have to, because it's a non-terminator, so I have to use a the production rule, that is the a's first production rule is ab, so I will use the production rule ab. Now because I'm using in order, so I will left to right, I'll go for the a, and when I see the a, that is a match because c a. But after that there's a b. B is not a match, so it's incorrect, so I have to backtrack this thing. So I can't do this thing, so I have to backtrack, right? So I have to use another production rule of the a, that is going to be this one, that is the small a, right? So I will use another production rule of a, that is small a, and because this is not a, you know, this is a terminator, so I have to chuck it with my input. It matches with the C and A in between. So C was already matched, A is now matched. Okay, here, and I'm done with this. So I go to the right side here, and I'm seeing this is D. D is also a match. So I got what? I got the match, right? So this is how the backtracking works. So when I got a match, I accept the token string. I say this is valid because it is syntactically correct. Now this recursive descent does not work when we actually have a left recursive grammar. So when you have a left recursive grammar, so this is not going to work. So we'll try to see what is left recursive grammar, and then we try to actually eliminate, we work on the elimination of the left recursive grammar, right? So this left recursion is to be eliminated, and we try to first see what is this left recursive grammar, and then we work on its elimination. So recursive descent uses what? It uses backtracking. It tries to find the leftmost derivation, you know, unless the grammar is ambiguous. And second thing is left recursive, which we'll talk it now. It finds a suitable parse tree, but it's rarely used because we got other ways, you know, other than backtracking, because backtracking is a bit slow. So we have the faster algorithms, we can work with them, we have better techniques. We'll talk about them later. The first thing would be now the left recursion. So we say that your recursive descent doesn't work if you have the left recursive grammar. Okay, so let's talk about in detail now the left recursive grammar and then how to eliminate that. So to understand what is a left recursion, let's take an example of a left recursive grammar. So let's say we have a left recursive grammar like this. So we got A goes to A alpha or beta. Now beta is here. Now you see left recursive grammar is something where we have LHS and the first non-terminator that are the same as of LHS. Now why is this problem? We'll talk about this. Okay, let's see. It's same as like we have a function call which calls to itself, isn't it? So what will happen if you have an some function, okay, and it calls itself, and then say for example it calls itself, and then it does some statements. Now what will happen when you call the A? It goes here, it calls itself, and it goes here, it calls itself, it goes here. So it's an infinite loop, isn't it? So this is kind of same. Now look at this, how this will happen. So when you try to do this production, it will go, say for example A gives you A alpha. Now you have to non-terminator A. Now alpha is a terminator, okay, no problem, but A is a non-terminator. You have to use some production. So if you use a production A alpha because you're the first production only, then you make it A alpha, and this is alpha again. Okay, now this A goes to A alpha, and this is alpha again. So this is kind of sort of thing where we have the A's comes up infinite times unless I don't use the beta. So maybe then I sometimes, if I use a beta here, now this will be a beta where it will end, but there will be infinite many alphas. So this can go infinite times, right? If I use here the beta, and if it doesn't match, and like we said in a recursive descent, if it doesn't match, I use a beta, so it can go to the beta only, or it may go to the alpha, A alpha, then go to the beta, and so in nutshell we can have infinite many alphas here, right? And with the beta. So this is going to be kind of beta and alpha star, right? Many alphas, either single beta, there is no alpha, or beta alpha, or infinite many alphas with it. So simply this is gonna be the A generates all strings starting with the beta and followed by any number of alphas. So this will not help. Okay, we may have this is the direct left recursion. We can have something else. We'll see, say for example this thing. Say for example this is say A goes to something else, say for example B, okay, alpha or beta. Now this B goes to A beta, for example. Now even though if we see that, hey, this is A and this is not A, so this may not be left recursion, but when we see the B, when we replace the B, it's replaced by the A itself. So when you substitute this B, it's gonna be like this. It's gonna be like A beta, alpha or beta. Now this is the leftmost production. The first production has the same variable, which is the leftmost variable, so left hand side. So this is the left recursive, this is again the left recursive grammar, right? Okay, so in general the formally we can say a grammar is left recursive if for all a non-terminal A such that A goes to asterisk A alpha for some set symbol alpha. Now asterisk A means here for example this situation where we have the B and the B goes to A again, so in 0 or 1 terms it goes to A. So here, like here, so either it's directly A, like in above example, A on the right side and on the left side, or with some one or more times you go deriving and you get the A back, so that A will be the left and the right. So that is, in that case, it's gonna be the left recursive. Okay, now this left recursion is definitely bad. Okay, and top-down parser cannot handle left recursions, but the good thing is we can recover this left recursion either by the hand, or there are many algorithms which automatically change left recursive to the non-left recursive grammar, or we can fix it using the hand. And the good thing is the best thing is we should use it fix it by hand, because programmer should know exactly what it is, what's going to happen, okay, what grammar it's going to use. So better is to convert that into the hand. So let's see how we do it. Let's write our left recursive grammar again. We say A goes to A, the same A here, same A here, alpha or the beta. Okay, now we want to change it. So how can we change it? So we got to rewrite it using the right recursion. So we use it using the right recursion. Okay, but remember, left recursion, right recursions are actually different, but we have to change it in a right recursion, but in a sense that it should not change the grammar. It should not be different. It should represent the same grammar. Okay, so we say here A goes to, I say firstly the beta, and then I say something like A prime. Okay, now this A prime gives me the alpha A prime or epsilon. Now if you look at this grammar, for example, we got an A, start an A, so it will derive into beta A prime. Now beta is there, then A prime goes to, okay, now this A prime we can use the alpha A prime. Okay, now this A prime again can go to alpha A prime and so on. So this can go on, but we can change it. A prime can go to the epsilon and so on, and A prime can go to epsilon, then it will be alpha A prime. So this will be, the language will be like kind of a beta and then many alphas, right? It's the kind of same language we had here, but the only difference is like a beta and alpha star, this is a kind of same thing, but we don't have an infinite loop that we will have. We don't have a left recursion here where there would be infinite loop, right? So it's the same language. Beta alpha star, it's the same, it's alpha star here, right? And it is same as above, but we have here what's called the right recursion. Okay, it's a right recursion. Okay, and this one was the left recursion, this guy. So but the grammars are equivalent because they generate the same, as you can see, beta times alpha star. I mean beta, first beta and then alpha and many times alpha, right? Let us take a more examples to get a hold on it. But before that, let us take it as our basis. So where you say A goes to A alpha times then or B beta, and this is converted to how we first write here the beta and then the A prime. Now A prime is what was there as an A, and then whatever is with this A, that is my alpha, and that stays here as the A prime. Then A prime comes back and the epsilon. Okay, so we use the same rule for whatever other things we have. Let's say for example we got this grammar which is left recursive differently because we have E here and E is here, so we're gonna replace it. Okay, so in this case we had an A and A, so we take up this was my A and this was my A, right? And whatever is left out is my alpha, that is alpha is plus T here, and the T is the beta, right? So how I change this, because this is the left recursive and this doesn't have a problem, so this will go like same, the second part will go like same, so this is to change. So we will say firstly E goes to, we'll take up the beta part first, like I did here. I took the beta part first here, then I take the beta part is the T, I took the T first here, right? And then I say here A prime, and in this case I will say E prime. Okay, this is the first thing. Now I have to specify the E prime. For E prime, what I did here, like A prime, I say first the alpha. So what is the alpha part here? That is plus T. Okay, so I will say plus T. Okay, and with it I have the A prime, so in this case I will have the E prime. Okay, and or I will have the epsilon. Okay, and the last part goes exactly the same way because this doesn't change, this has no problem of recursion, so I say ID, T goes to ID or E. Okay, same way. So this is the non-recursive where I have the sorry, it's not non-recursive because it is recursive, but it is having no left recursions now. Okay, so if we say that if we have an A gives A, say for an alpha 1 or A alpha 2 or so on up to the alpha A alpha M. Okay, now and then we have also the beta 1, the beta 2 and so on up to the beta N. So we will transform it to A. We'll transform it, we get the beta up front, so beta 1 then A prime. Okay, or beta 2 A prime and so on up to beta N A prime, and then we define the A prime as that we got the alphas 1, alpha 1 A prime and alpha 2 A prime and or so on up to alpha M A prime, and we also got the or the epsilon. So the general algorithm to remove the left recursion is what? There is several improvements to the method. We will see this. So we have here A gives A, then A1, A2 and so on. Then we're going to beta 1, beta 2 and beta N, where A is the left recursive non-terminal. This is the problem we have. The A's, these are the left recursive non-terminals, and the small a is a sequence of non-terminals and terminals that is not null. In this case we had an alpha, right? So A should not be epsilon. And beta is a sequence of non-terminals and terminals. So beta is anything like B1, B2 we saw here, beta 1, beta 2. This could be anything which that does not start with the A. It should not start with the A. It can contain A, but it does not start with the A, right? So we have to replace the A production by the production. So we're gonna change it. Replace the production A by the beta 1, that is a sequence of non-terminal terminals that does not start with A, and so on, beta 2, beta, and then we have an A prime, that's a new non-terminal, and we define it like this, where we have the A1s and A primes, A2 and A primes, and then these A's are the sequence of non-terminal terminals that is not null, and then we have on the and an epsilon. So this newly created this A prime is called the tail or the rest. Okay, now we have seen the recursive distant parsing with backtracking, and we see the how to do the eliminate the left recursion and all those things. Now it's a kind of slow thing, and because you have to backtrack all the time, because you have to you don't know which production to use. So that's why we need some kind of magic. That's what's called the prediction. So we do what's called the predictive parsing next, which will try to predict, and which is deterministic. If you see the background was non-deterministic, you never know which production to use. And now in the predictive parsing, we exactly know which production rule to use. So that we will use next. So stay tuned for next video. Until then, ma salama.